Hi, in this video, we're going to finish our discussion of section 14.6, talking about tangent planes and normal lines. Now, with techniques we've learned so far, we can write the equation of tangent planes in a bunch of situations. But we would like to use our new knowledge of the chain rule and directional derivatives, specifically the gradient, to simplify this idea. So the goal is to find the equation of tangent planes, of a tangent plane to a surface. At a point. And just to recapitulate or refresh your memory, in Calc 1, in AB, whatever you took, we have a curve and a tangent line to that curve. In multivariable, in the class we're in right now, in Calc 3 or Calc 3D, we're talking about a situation where you have a surface, and at some point on that surface, we're getting a tangent plane that's resting on top of that surface, so to speak. Or it could be below, but in this one, the way I'm seeing it, it's on top. We're going to rewind back to 2D to look at how we can use the gradient to come up with normal lines there. Because for a plane in 3D, we want to find a normal vector. That's more important than these tangent lines and tangent vectors. If we want to actually talk about the planes equation, we need the normal vector there, not any sort of tangent line. No one tangent line can define the plane because there's infinitely many lines that live inside the plane. So we're going to go back to talk about normal lines and tangent lines on a curve in the 2D space, because we can use those techniques to go to a 3D surface eventually. So it's always going to be confusing because we're going to be jumping back and forth between dimensions, so feel free to, rewind the video. All right, so if we're given a surface, and so the surface is always going to be, z equals some function of two variables. So we're talking again about a 3D surface because there's three variables all over this equation, but there's only two inputs, one output, right? So that's what makes it a surface. It's going to be a function of the two variables. And we have such a surface like the one I just drew. So we're going to draw our surface, and we're going to try to make it, we're going to find a level curve, which is back in chapter 14, section 1, so you can go watch that video if you wanted to, or just glance over the definition. F of xy equals some constant c, or you can watch, just video should give you an idea. So the level curve is picking out spots on this surface that all have the same height in the plane. So I'm just trying to imagine something slightly more interesting here. And that all has some sort of specific height c. So once we've set the z variable equal to c, we have a curve. That's why we're calling it a curve. It's no longer a surface. It is literally just this trace of points that we were using isotherms or areas on the map where the elevation is the same. To get a 2D, because it has two variables now, and we can project it into the XY plane and see that we have basically some sort of potato blob type shape. This level curve can be parameterized, which is something we discussed in chapter 10. Parameterized, yeah, I'm right. Or even chapter 13 as a function, as a vector function. R of t equal x of t I plus y of t in the j. Right? You could write it in component notation, but this is producing an x and y coordinate for every single time. Okay? So we can, it doesn't have to be a particle motion, but you could imagine a particle walking in this direction or an ant walking along this curve at specific times. So we found a vector function that talks about this, and therefore we're going to combine all this information. So f of r of t equals c, right? Or if we thought of that as f of x of t, y of t, right? Those t values could go into f and give us this equation where now f is a function that depends only on t for this specific height. This would not work to talk about f all over the place. This works to talk about f's locations along this level curve. X of t is a function that's defining the x coordinates along this level curve. Same with y of t, okay? This is not changing the function totally. This is just for this one level curve, okay? You'd have to do this separately for each level curve. Why are we writing it like this? Because this should look familiar with our chain rule diagram. Hint, we could take the derivative of both sides, not using implicit, just using the chain rule now. And we would see that the derivative of the right-hand side is 0. The derivative of the left-hand side is f prime of this stuff, right? But what should that derivative actually look like? What should the derivative of this with respect to t, I guess I should write it like this, it's more accurate, look like? Well, we have to use the chain rule. It would be partial f partial x times dx dt plus partial f partial y dy dt. And that would all still equal 0. Now, this is not the type of trick that's easy to notice, but someone did notice it. What's on the left kind of looks like an x thing with an x thing plus the product of a y thing with a y thing. So some ingenious mathematician thought we could decompose this into, I don't know why I'm switching between components and not, this vector dot product with this vector. And we notice that these two vectors, whoops, that's a t, their dot product is 0. Now, what are these two vectors? Why are they relevant? Why are they useful? Well, the one on the left is the gradient vector for f at xy. And the one on the right would be the derivative of the position function for that level curve projected into the xy plane. And that is always true. If you define a parameterization of a level curve, it will always be always have a dot product with the gradient that results in 0. Now, what was a dot product equals 0? I guess we'll just start talking about what this means. So, what this means. Why are we doing all this? And again, nothing we've done so far might be that relevant to you. I mean, everything we talked about with level curves, you're like, well, I know how to make a tangent line and I would know how to make a normal line. The idea is how we're going to apply this into the 3-dimension situation. So, what this means. 1. R prime, this is always true, gives what on that level curve? R prime is the tangent line, gives the tangent vector, vector's slope, for the level curve. Right? At any point, R prime is that vector. 2. Let's think about what that dot product being 0 means. 2. Let's review that when a dot product equals 0, vectors are what? So it's your last chance to think about this. What property do the two vectors have? They are orthogonal. I hope you didn't say parallel. That's if the cross product is 0. And again, we don't usually even use it that way. So the two vectors are orthogonal. So therefore, what is the gradient vector giving us? What vector is orthogonal to the tangent vector? And this might, you go back one page in the slides, go back one page in your notes. So the gradient vector of f is the normal vector to a level curve. It's still to a level curve at a point. So that would be the gradient. Notice the gradient is still a vector. I'm going to blow up that image really quick because I'm not sure it's easy to see. So if we have x and y, and we're looking at the surface, right, r prime is the tangent vector here. A measurement of the slope of that line. In vector form, the slope's a little bit different to calculate, but r prime is the tangent vector, and the gradient is always perpendicular to that. So this also gives us a really interesting conclusion. It tells us that, in fact, if I wanted to travel up a hill, 1, this shows the result from the previous videos, that, I guess I'll end here, that the gradient vector maximizes change. So we're finally showing you that result, if you really were suspicious of it. If I have level curves here, and each of these level curves represents, the change in a mile, the gradient is pointing against the level curve at every situation, or against the level curve here, and it would show you the pathway to maximize your height. The pathway to maximize the change in height would move against the level curve, because moving tangent with the level curve, if you're on the level curve still approximately, means your height's not changing. So how to change your height the fastest? You'd want to move away from the level curve in an orthogonal motion. That's the idea of why we're using the gradient as a vector that maximizes the change in height. And we also have two results. So in general, the gradient of f of xy, a 2D vector, right, a derivative with respect to x and the derivative with respect to y, is the normal vector to a level curve the big conclusion. So what if I extrapolated this into a third dimension? Again, confusing. This would be a third dimension in terms of f, which will mean 4 dimensions total. Well, that's why it's really hard to think about. This is going to be the normal to a level surface. Again, if you're not that fresh on chapter 14, section 1, level surfaces are based on equations like w equals f of x, y, z, and there w is the dependent variable on 3 independent ones, like temperature at a point in space. Okay, maybe the gravitational force at a point in space, the magnitude of the force, maybe the potential energy at a point in space. And that would be a 4-dimensional graph, which doesn't make sense to our 3-dimensional experience. But this, if we replace w with a constant, now there's only 3 variables, and now we'd have a level surface. So we would define the points in space, the points in 3D space, where all of the points in 3D space where they all have the same potential energy, the same gravitational force, the same temperature. All the points in your room that have the same temperature would be some sort of 3D surface. That's what a level surface is. Therefore, we can use the gradient of f to define tangent planes and normal lines to a 3D surface. Notice that both of these, a tangent plane and a normal line, they both require a normal vector, right? Lines is going to be more clear why we need a normal vector. Both need a normal vector. Why does a tangent plane need a normal vector? I refer you to the very first image I drew over here, right? We need a normal vector to talk about this plane accurately. The plane equations are given by a normal vector and a point. So let's see this in action. Find the tangent line. Let's slow down and go back to 2D real quick. Or sorry, tangent line and normal line. I'll show you what I mean. Normal line to x squared minus y squared equals 16 at the point 5 comma 3. So we're going to kind of like cheat the system, right? This whole thing, that's a 2D curve. In fact, if you remember your pre-calc, that's like a hyperbola. It's a 2D hyperbola. But we're going to cheat by making this a level curve. Here's how to apply everything we've just been talking about of a 3D surface. So it's like picture x squared minus y squared equals z, or f of xy equals x squared minus y squared, and then f of xy equals 16, right? That's a level curve. That's exactly what we've talked about. So this is a level curve of that f of xy surface. Okay? So the gradient of f gives normal vectors to the level surface. A question that comes up sometimes when we're talking about this is, well, wait, did it really matter that it was 16 there? No, it does not matter which level curve we're looking at. Which level curve, sorry. Does it matter that it was 16? No. The whole technique works whether it was 16 or 20 or 15 or negative 500. The technique will always give us a level curve, the normal vector for a level curve or the normal vector for a level surface, regardless of what kind of level height you're looking at, what kind of height you're setting it equal to. So what is the gradient of f here? This should be relatively easy to calculate. We're talking about the derivative with respect to x, and then the derivative with respect to y. Okay? That's going to be a normal vector. This is a normal vector. Let me reiterate. For any height, for any level curve, x squared minus y squared equals c. Any constant. So specifically, this guy, when I actually plug in the point they wanted, I get 10 comma negative 6 is the normal vector at 5 comma 3. So the slope of the normal vector is negative 6, always the y over the x. And the tangent slope would be 10 over 6, or 5 over 3. I guess I could have reduced the other one too. Okay? Now, it's not that impressive because you guys have been working with x squared minus y squared equals 16 for a while. You could do this problem in Calc 1 just using implicit differentiation, or now that you know how to use the chain rule to make implicit easier, even that, right? That would maybe wipe this problem out shortly. So let's see. The tangent line would be y minus 3 equals 5/3 x minus 5. And the normal line would be y minus 3 equals negative 3/5 x minus 5. Okay? Just to finally put the fine point on this. Now, that's our situation in let's call it 2D because we're talking about a level curve. But again, we're reimagining this 2D level curve or this 2D curve as a level curve of a 3D function. That technique is going to be much more useful in this situation. So find the normal vector to this ugly looking guy. Negative x squared plus y squared minus z squared equals 4 at 1, 3, 2. All right, now, very first thing, you could think about what kind of surface this would produce. Okay, we notice there's all three letters are squares. We could notice that only one of them is positive, and so you would be right if you said this was some sort of cone. That doesn't really matter for how you would do the problem. We're talking about finding the normal vector to a cone, to the surface of a cone. So that might help you visualize it. This would be really hard, right? If I asked you to do this back at the beginning of the chapter, it might be impossible. Some of you might be still looking at it like that. But this keyword, normal vector, you should always be thinking of as our gradient. We need to figure out some sort of function where the gradient could be used. Again, the same exact trick will apply. We're going to make f of x, y, z, I don't know why I made it capitalized, it doesn't matter, equal the non-constant part. Because now this cone is just a level surface of this capital F function. Now, this capital F function is a 4D function. And again, I don't know what it looks like, but I know its level surfaces look like cones. Equals 4 is a singular level surface that contains 1, 3, 2. Okay, that's the level surface that contains our key point. And it's a 3D situation. This guy is 3D. It's a cone. It's the one we were just talking about up there. Okay, that's why this technique works. And now everything else is really easy, but I want to make sure you understand the concept, or at least try to make sure. So, what does gradient of f produce? This is going to give us a 3D vector that's normal to capital F of x, y, z. Level surfaces. That's why it will maximize the rate of change of the output, the W coordinate, the temperature, the gravitational potential energy, whatever. Okay, so it's a 3D vector. What do you get when you do the normal vector here? Differentiate x, differentiate y, differentiate z. 3, 2, 1. Getting negative 2x, positive 2y, negative 2z. Okay? And therefore, if I take this gradient and plug in 1, 3, 2, I get negative 2, 6, negative 4. That's the normal vector to negative x squared plus y squared minus z squared equals 4. At 1, 3, 2. That's all we've done so far. We've motivated it, and I hope it's been somewhat clear. And now we're going to put the finishing touch on this by looking at our normal vectors as part of tangent planes. So for tangent planes, let's refresh with, we're talking about a normal vector, usually with numbers A, B, and C, and a point with 3 coordinates, because we're talking about a 3D coordinate. And planes are only really interesting, or only really a thing, once you get into 3-dimensional space, because everything else is happening inside a plane in 2-dimensional space. And we have this equation. This is our standard starting point for a plane. There's other ones where you can solve out for what the constant d is, but this is the normal go-to. And for our tangent planes, for our tangent plane to a level surface, we're going to be getting these numbers A, B, and C from a gradient vector. So for tangent planes, this normal vector is equal to the gradient vector. Okay? Of usually some other function, some 4D function f. Okay? And normal lines in 3D space, we're going to be talking about, we use that same normal vector, still A, B, C, and we still have the same point. And then the easiest way to turn that into an equation of a line, remember that we don't have one sort of equation of a line. We can either do the vector equation of a line, we can do the parameterization of an equation of a line. It's like x naught plus at, y equals y naught plus a bt, z equals z naught plus ct. You could do the symmetric equation of a line, x minus x naught over a, y minus y naught over b, c minus c naught, oh man, z minus z naught over c. Those letters are too close together for me. All right, you could use either one of these to figure out, to make the equation of a 3D normal line. Okay, and for tangent line, for normal lines to a 3D surface, we can get that same normal vector from a gradient. XYZ equals -4 at the point 2, -1, 2. What's the first step? The first step is figure out what f of xyz is going to be. Give me a 4D function where this red surface at the top would just be one level surface. This is usually really easy. Just take one side of it. You could get 0. That's another strategy. It really won't matter, right? There's lots of 4D functions that will have the same level surfaces, the same way there's a lot of 3D functions that have the same level curves. Or to go down even another level, there's a lot of functions in general that have the same derivative. That's the same kind of analogy, right? X cubed plus a constant will always have the derivative 3x squared, regardless of what that constant is. So much to the same way, no matter what capital F you're starting with, you're going to all find the same gradient of that capital F. Go ahead, find that for me. 3, 2, 1. We haven't used basis notation in a while, so derivative with respect to x in the I direction plus the derivative with respect to y in the j direction plus the derivative with respect to z in the k direction. So that's the normal vector to the level surfaces of capital F, of which our red function happens to be 1. Plug in the point, 1 comma, or 2 comma negative 1 comma 2, and we should get what? 3, 2, 1. We get negative 2 in the I, plus 4 in the j, minus 2 in the k. And then we use this to generate our normal vector. You can just use that. You can use that as your normal vector. But sometimes we might want to simplify it, like when they all have a common length or a common factor, I guess is what I really mean. You could divide everything by 2 or negative 2. Like 1 comma negative 2 comma 1 also works, just to be clear. Now, if you want to not overcomplicate things, so to speak, feel free to use the non-simplified version. But then the planar equation, the tangent plane would be x minus 2, 1 times, plus negative 2, I guess I'll write minus 2 times y plus 1, plus 2 times, 1 times z minus 2. So it's really important to keep track of what's supposed to go where, right? These numbers are all coming from the normal vector, and these numbers were coming from the point. I almost got that mixed up. Again, please, when you're writing, distinguish your z's from your 2's. It's always a big issue for students. And you could solve this out. Oh, equals 0. When you have a planar equation, it's always going to be one equation for a plane. And my normal line, I prefer the parametric one, so I'm going to do x equals two plus t, y equals negative 1 minus 2t, z equals 2 plus t. Where these numbers come from the point, and these numbers, the coefficients, come from the normal vector. Okay. So this video is already pretty long. I'm not going to do another example. It's all just using the same techniques we learned in the previous videos. Gradient vectors, but just using that as the normal vector. Finding the full potential of these gradient vectors. Thanks for watching, and I'll see you in the next video.